Today you discuss calculation of number of spectral lines. Calculation of number of spectral lines. For a sample of atom, for a sample of atom, for a sample of atom, it means many atoms. Many atoms. For a sample atom, you take a sample of atom. A sample of atom means it consists many atoms. Okay, case 1. Case 1. If electrons de-excited to ground state from nth level, in the first case, electron is excited to ground state from nth level. How many spectral lines are formed? In such case, maximum number of spectral lines is equal to n into n minus 1 by 2. In such case, maximum number of spectral lines is equal to n into n minus 1 by 2. For example, value of n, number of spectral lines, number of maximum spectral lines. Okay, first one, n is equal to 5. Therefore, 5 into 5 minus 1 divided by 2. So, number of spectral lines 10. These 10 spectral lines belong to various series. Okay, Lyman series, Balmer series, Fashion, Bracket series. Next, when n is equal to 4, number of spectral lines 4 into 4 minus 1 by 2. That is equal to, this is 3. This is 3. 3 into 4, 12. 12 by 2, 6. When n is equal to 3, number of spectral lines 3 into 3 minus 1 divided by 2. Okay, 3 minus 1, 2. 2 into 3, 6. 6 by 2 is equal to 3. When n is equal to 2, 2 into 2 minus 1 divided by 2. That is equal to number of spectral lines 1. Okay. This is applicable to when electrons are excited to when electrons are de-excited to ground state from nth orbit. If you take sample of hydrogen gas, this formula holds good for sample of hydrogen gas when electron de-excited to ground state from excited state. Okay. Now, per suppose electron in a given sample, electrons de-excited to ground state from fifth fifth orbit. Okay. Number of lines in a Lyman series. Number of lines in a Lyman series. Number of lines in Balmer series. How to calculate number of lines formed in a Lyman series? How to calculate number of lines formed in a Balmer series? How to calculate number of lines formed in a Fashion series? Therefore, number of lines in a Lyman dash in a Balmer dash in a Fashion dash in a bracket dash in a P fund. Electron de-excited to ground state from fifth orbit. Number of lines formed in a Lyman series. Number of lines formed in a Balmer series. Number of lines formed in the Fashion series. This is done by using sigma n2 minus n1. That is equal to 5 minus 1. That is equal to 4. Sigma 4 is equal to 4 plus 3 plus 2 plus 1. So total lines 10. In a Lyman series, 4 lines are formed. In a Lyman series, 4 lines are formed. In a Lyman series. 3 in a Balmer series, 3 lines are formed. This is Balmer series. Okay. In a Fashion series, 2 lines are formed. In a Fashion series, 2 lines are formed. In a bracket series, 1 line is formed. In a bracket series, 1 line is formed. Electron is de-excited to ground state from fifth orbit. Number of lines in the Lyman series 4. Number of lines formed in Balmer series 3. Fashion series 2. This is 1. Total lines 10. In a P fund, number of lines formed 0. Number of lines formed 0. Okay. Lyman, Balmer, Fashion and a bracket. P fund 0. Okay. Another example. Electron de-excited to electron is present in fifth excited state. Okay. Number of spectral lines. 6 minus 1, that is equal to sigma 5. Since fifth excited means electron present in sixth orbit. Okay. Fifth excited means electron is present in the sixth orbit. Okay. 6 minus 1 is equal to sigma 5. Sigma 5 is equal to 5 plus 4 plus 3 plus 2 plus 1. Okay, 5 plus 4, 9, 9 plus 3, 12, 12 plus 2, 14, 14 plus 1, 9, 9, 10, 10 plus 3, 13, 13 plus 2, 15. Number of spectral lines, 15. In a Lyman series, 5. In a Lyman series, 5 spectral lines are formed. In a Lyman series, 5 spectral lines are formed. Okay. In a Balmer series, 4. In a Fashion series, 3. In a bracket series, 2. In a P fund series, 1. Okay. In a P fund series 1. Okay, next. In hydrogen sample, all electrons in the fifth excited state. Find lambda of longest and the shortest and longest lambda in a visible region. So in hydrogen sample, all electrons in a fifth excited state. Fifth excited state. Okay, find lambda of longest wavelength, lambda of longest line. Okay, find lambda of longest and shortest line. Shortest line. Okay, and lambda of longest line in visible region. Lambda of longest line in visible region. But find three questions here. Lambda of longest line, lambda of shortest line, and lambda of longest line in the visible region. Okay, therefore sigma 6 minus 1, that is equal to sigma 5, that is equal to 5 plus 4 plus 3 plus 2 plus 1. Okay, ఇక్కడ 5 lines. This is Lyman, Balmer, this is Passion, this is Bracket, and this is Pfund. Lyman series, Balmer series, Passion, Bracket series, and Pfund series. So, in a Lyman series, transitions 5 to 1, electrons present in a fifth excited state and 6 to 1, 5 to 1, 4 to 1, 3 to 1, and 2 to 1. Total 5 lines. In Balmer series, 4 lines. These are 6 to 2, 5 to 2, 4 to 2, 3 to 2. This is 4 lines. These are 4 lines. Okay. Fashion. This is Lyman. This is Balmer. This is Lyman series. This is Balmer series. And this is Passion series. 6 to 3. Okay. 5 to 3. Okay. 4 to 3. This is Passion. This is Passion series. Okay. Next, Bracket series. 6 to 4, 5 to 4, 2 lines. Okay. Pfund 6 to 5. Okay. Question number 1, longest wavelength 6 to 5. Longest lambda 6 to 5. Because this is present in Lyman series, present in UV. This is visible. These 3 are present in IR regions. Okay. 6 to 5 longest lambda. Shortest 6 to 1. shortest wavelength, shortest lambda 6 to 1. In visible region, longest wavelength 3 to 2. In visible region, longest wavelength 3 to 2. Shortest wavelength 6 to 2 in visible region particularly. Okay, particularly in visible region, shortest wavelength 6 to 2, longest wavelength 3 to 2. In overall, longest wavelength 6 to 5 and shortest wavelength 6 to 1. Okay, next. Okay. N minutes second. N minutes second. Next, case 2. When electrons drops to lower orbit other than n is equal to 1. In previous case, electron is de-excited to ground state. From higher orbit, number of spectral lines is equal to n into n minus 1 divided by 2. But in such case, when electron drops to lower orbit other than n is equal to 1. Number of spectral lines is equal to number of spectral lines is equal to delta n into n plus 1 divided by 2. Okay, delta n into delta n plus 1 divided by 2. Sorry, I made mistake. Delta n into delta n1 plus delta n plus 1 divided by 2, where delta n is equal to n2 minus n. N2 is higher orbit. Delta n is equal to n higher orbit minus n lower orbit. Okay, delta n is equal to n higher orbit minus n lower orbit. N higher orbit minus n lower orbit. Okay, for example, electrons are de-excited to second orbit from fifth orbit. Number of spectral lines is equal to delta n plus 1 divided by 2. Delta n is equal to 5 minus 2, that is equal to 3. Therefore, 3 into 3 plus 1 divided by 2, that is equal to 12 divided by 2, 6. 12 divided by 2, 6. Okay, 12 divided by 2, 6. Next, 12 divided by 2, 6. Next, case 3. In case of isolated hydrogen atom, isolated hydrogen atom means only single atom. Previously we discussed Sample of hydrogen gas. Sample of hydrogen gas means that sample has many hydrogen atom. If you take isolated gaseous atom, if you take only one hydrogen atom, okay, when electron is excited, when electron is excited, when electron is de-excited, okay, number of spectral lines is equal to n minus 1. Okay, for example, electron present in fifth orbit, number of spectral lines 5 minus 4, 4 minus 3, 3 minus 2, 2 to 1, 5 to 4, 5 to 4, 4 to 3, 3 to 2 and 2 to 1. Number of spectral lines 4. Okay. These are the calculations about calculation of number of spectral lines in hydrogen spectra. Okay. Understand? You understand? Okay, right. G. Excitation energy. It is the energy required to excite an electron from first level to nth level. It is energy required. It is energy required. Excitation of electron from first orbit to nth orbit. First orbit to nth orbit. This is excitation energy. Therefore, excitation energy is equal to En minus E1. Excitation energy is equal to En minus E1. Okay. Excitation energy is equal to En minus E1. Energy of En is equal to minus 13.6 into Z square divided by N square electron volt. E1 is equal to minus 13.6 into Z square divided by 1 square electron volt. Okay. En minus E1. En minus E1 is equal to minus 13.6 into Z square divided by N square plus 13.6 into Z square. Okay. Therefore, En minus E1 is equal to by 1 square is equal to 13.6 into Z square 1 by 1 square minus 1 by N square. This is the excitation energy. This is the excitation energy. Okay. First excitation energy means electrons excited first orbit to second orbit. Second excitation energy means electron excited to 1 to 3. Third excited energy is equal to electron excited to 1 to 4. Fourth excitation energy is equal to electron is excited to 1 to 5. Okay, find the second excitation energy of Li2 plus. You understand? Completed. Okay. Find second excitation energy of Li plus 2 ion. Find second excitation energy of Li2 plus ion. How to calculate? excitation energy is equal to 13.6 into Z square 1 by 1 square minus 1 by N square. 1 by 1 square minus 1 by N square. Okay. Second excitation energy means second excitation energy is equal to 1 to 3. 1 to 3. Electron is excited to third orbit from first orbit. Yes or no? Therefore, excitation energy is equal to 13.6 into 3 square 1 by 1 square minus 1 by 3 square. Second excitation energy is equal to 13.6 into 3 square. Atomic number of Li plus 3. 1 by 1 square minus 1 by 3 square. Okay, that is equal to electron volt. 13.6 into 9. Okay, into 1 minus 1 by 9. That is equal to 13.6 into 8 electron volts. Okay, this is the answer. Excitation energy is equal to 13.6 into 8 electron volts. Okay, you understand?